Now we will search for limit points more collectively. Namely, we'll be calculating so-called derived sets. So the used notation in there is that if S is some set, then SD is the derived set of it, which simply means the set of all limit points of S. Let's consider the first example, which is quite similar to the previous video. Maybe let's see the situation on the axis. So we have again some interval between 2 and 3. When in the set itself we have 2, do not have 3, and we have of course everything in between. Let's consider the points inside the interval. Because of this fact about neighborhoods, when we pick anything inside there, then easily finding some neighborhood to it, maybe for this point or this point, we cannot make a situation when we do not have the common points with this interval, because we are simply inside of it. So for all the points that are not 2 and 3, we always need to contain something on the left and right hand side from it, so there is no question about it. Actual similar situation for 2, because no matter how small epsilon we will find, there will be some common point on this right hand side from 2, somewhere there, even though the left hand side will be empty. And the fact that 3 is not there doesn't change it that its neighborhoods also will always have some common points with this interval. So simply taking a derivative of this set fulfills us this whole with non-existent 3, and it closes this interval to be just 2 to 3. We cannot add anything else because, for example, when there is 2, if you would like to add any point on the left from it, for example here, you can simply find, let's say, half of this distance between this point and 2 for the epsilon when the neighborhood will contain no common points with this interval. So simply in such situations, just the missing number on the borders or in the holes inside of the interval will be added alongside this operation. With first example done, let's move into the second one, which is very similar. Here we have almost all real numbers. Yeah, of course, R means just real numbers, but we have one number removed, namely pi. So our set is the whole axis there, but we are missing only one point in it, which is pi. So using similarly the neighborhoods argument, whatever we pick besides this pi, we simply see that all neighborhoods will have common points with this set. Actually, the only non-common point with this set is the pi itself, but when we pick pi as the element number to consider, then again, all of its neighborhoods, no matter how small the epsilon, will have common points with our set, which in this case is actually obvious even without any graphics, because all real numbers except pi are in our set. So if we will set any non-empty neighborhood, it must contain the common points, because they are just different numbers than pi. So similarly to the intervals, it just fills the hole in this set. So the pi is added and the answer to this exercise are just all numbers. So full R. Now a very different situation because our set is not interval or the full axis, almost full axis anymore, but just 4 elements. We have 4 numbers in our set, 0, 1, 2 and 3. So if we would like to see them on the real line, just like we did before, we will have 0, 1, 2, and 3, for example, like that. And only these 4 points are inside our set. So now let's think one by one. Is 0 a limit point of the set? Not really, because actually we can very easily find a neighborhood that has no common points with this set. If I would take large enough epsilon like there, for example, then yeah, this neighborhood contains common points, namely 0.1. But if I would take something between 0 and 1, for example, such value, let's say it's half, then we have the neighborhood of 0 that contains no common points with this set. because of course points of questions are except the point we are checking for being the limit point. So except the 0, there is nothing in this neighborhood that is contained in our set of question, because all other elements are 1, 2, and 3 that are outside of it. And with exact same argument, none of these 4 points is the limit point of this set. So we need to remove 0, 1, 2, and 3. So basically all of this set. And similarly, none of the points outside, besides 0, 1, 2, and 3 are the limit points of this set. Because if we take anything outside of these 4, let's say something here like 3.5 or something, we can again easily see neighborhood that contains no of these elements from this set. For example, this neighborhood contains nothing in there, and we can easily find many such neighborhoods, actually infinite number of them. So what does it mean? Well, if derived set is the set of all limit points of some set, and we just see that there are no limit points to this set, then simply the derivative of this set is the empty set. So there is nothing that fulfills the definition. Now the quite similar situation, we want to find the derived set to all of integers. So this time again, our set has infinite number of elements, not just some 4 chosen points, but just like in the previous example, they are separated by these intervals. So we have, for example, 0, 1, 2, 3, -1, -2, -3, and of course z denotes all integers, so up to infinity and minus infinity both ways on integer values. But just like previously, any of these integer points is not the limit point of this set, because we can easily find the neighborhood that contains nothing common with our set of all integers except the point in question, for example this for 0 value. And similarly, any value in between these integer values, for example this number, you can easily find neighborhood that has no common elements. And if it's in between integers, there is always enough space up to the next integer. You can divide by half, and that's your epsilon. So even though this time we have infinite number of elements in our set, the derived set, from the same reasons, is still just empty. And the very last one after all these should be quite easy. Let's denote somehow the situation. So in our set we have numbers going from minus infinity up to -1. So let's denote this -1, but without it. So everything in there is in our set. Then we add to it another interval from -2 up to 2. So let's denote somewhere 2. Everything in between there is in our set again, but without 2 as well. And then the set continues from 7 up to infinity. So it is very similar to the first examples. See that just like there, we have some holes, like here. Just one value is removed from this to be the longer interval, similarly there and there. So for example, from this point, it is easy to find neighborhoods with common points. Actually, each of them will have common points on the left and right hand side from it. Here only on the left hand side, but that's enough. And similarly here on the right hand side. But that's enough again to be non-empty common elements. So basically, we just fill these holes on the borders of our intervals that constitute to this set. So after adding the missing -1, 2, and 7, we have the set that goes from minus infinity up to 2, because -1 in the way is added. This 2 itself is included as well. And similarly, the other interval starts with 7 now included up to infinity.